J. Marx is a Caltech experimental particle physicist who in recent decades has been involved in several of the highest profile physics projects in the country and was recently the executive director of the Laser Interferometer Gravitational-Wave Observatory, LIGO.
Okay, as we try to get this going, I'm not an artist, I'm a scientist, but I want to tell you about something that, like art, I hope you'll think of as a very human enterprise, this time involving tool building and curiosity. I promise there's only one equation, and I promise you'll all understand it. Okay, great. So I'm going to tell you about the discovery of gravitational waves, which you've heard mentioned by a few others, from merging black holes. Just a comment, thank you all you taxpayers.
You're welcome.
This research cost you about $1 billion over the last 25 years.
It was worth it.
And worth it.
Hey,
Thank you.
Okay.
I want my money back.
So let's start here. I can make this work. Long ago in a galaxy far away, there were two black holes who'd been circulating around each other for hundreds of millions of years, slowly emitting energy, finally coming close enough to merge, if we wait for a few minutes, into a larger black hole. This happened 1.2 billion years ago, 1.2 billion light years away from us. And the strange distortions you see are due to the strength of the gravitational field bending light, and that's why the positions of the stars seem to change. Okay, so here's what happened on Earth. It was September 14, 2015, when the gravitational waves from that event, 1.2 billion light years away, swept across the Earth and were detected by LIGO, which I'll tell you a little bit about. LIGO is a huge physics experiment, even though it's now leading into a new kind of astronomy. It involves, right now, about 1,000 scientists and engineers from almost 100 universities and labs from something like 16 countries. And so on the human level, it's this wonderful international collaboration of people trying to work together to do something incredibly difficult and amazing. On February 16th, LIGO and our colleagues at Virgo, sister observatory, announced this discovery. It was on the headlines of papers all over the world. My daughter was in Cartagena, Colombia, woke up and saw it right on the front page, which was great. What was discovered? Well, first of all, this was the first direct observation of these gravitational waves that I'll tell you about in a few minutes. That they were predicted by Einstein in his theory of relativity, theory of gravity, 100 years ago. It was also the first direct evidence that black holes exist. You saw this picture previously of matter going around black holes and making jets. And people have seen the particles from those jets, X-rays from the stuff swirling around, but never seen any signal from the black hole itself. In this case, this is what we've seen. Of course, we saw that black holes can exist in pairs, in binaries. But mainly, as you'll see, this discovery marks the beginning of a whole new kind of astronomy, not using electromagnetic radiation, radio waves, light, gamma rays, and so on, but a whole new kind of signal. Gravitational waves. We got a lot of, there was a skit on Saturday Night Live, so that was, we got congratulations from the president, and even Albert. Okay, so here's the hard part, what are gravitational waves? Well, first of all, you have to realize that according to Einstein, the fabric of space-time, let's say space itself, is dynamic. And what I usually try to think about is sort of a trampoline with a bowling ball in the middle. And the weight, the mass, changes the shape of space, it warps it. And if you think about that picture and imagine a ping pong ball rolling near that bowling ball, it'll curve. There's no force. The ping pong ball is just following the curvature of space. That's Einstein's interpretation of gravity. Now you can imagine if you take that bowling ball and bounce it up and down, you're going to make waves in the trampoline. In the real world, that's the analogy to gravitational waves. These are ripples in the very fabric of space and time. They travel outward from the source at the speed of light. That's why it took 1.2 billion years for that signal from those merging black holes to reach us. And these gravitational waves have a strange effect on everything. If a gravitational wave is coming at you, it will first stretch you vertically and squeeze you horizontally, and then be reversed as the wave comes by you. And that's a phenomenon that allows us to actually detect these things. So let's see if this thing works. Okay, so now you can imagine a gravitational wave going into the page. Turn off the sound because I don't want any sound here. Come on, you can do it. Oops, sorry about that. Let's try this again. Here it goes. Stretch, compress. That's the effect of a gravitational wave. And so we can build instruments to try to observe this. First of all, let's talk about what could cause these things. Any moving mass that's accelerating, like if I do this, I'm making gravitational waves, but they're so incredibly weak. I mean, it's just, you never see them. But some of these incredibly violent events in the universe, exploding stars, colliding black holes, things like that. We have huge compact objects, the massive stars, spinning together at half the speed of light and merging. There's enough sort of swirling around in space-time to create gravitational waves that are barely observable on Earth after a lot of effort. In fact, to give you a sense, that pair of merging black holes I showed you earlier, a billion light years away, each of them tens, I'll give you numbers later, tens of the mass of the sun, stretch and compress space, like that balloon of Einstein, about the billionth of the size of an atom.
Whoa.
That's the challenge. How do you measure that?
Wow.
It's crazy. You know, first time I heard about LIGO, I was on some review of LIGO, and I went and told my friends, this is nuts. There's no way it can work. But it works. In fact, LIGO does this by using instruments that are miles in size to measure something, a billionth the size of an atom. It's sort of this paradox of the way nature works. The smaller something you want to measure, the bigger you have to make the instrument. And LIGO is, I think, the most precise instrument ever built. And it's based on the interference of light waves. And so I'm going to try to show you an animation to explain how this works, if the animation works. Here's a laser beam being split, going along two paths, bouncing back and coming together. And let's ignore this for a second. We'll look at this in slow motion. There we go. So here's a light beam. It's split into two parts. It's going down two arms of an L-shaped instrument with a mirror at the end. The light bounces back from both arms, and if the path along these arms is exactly the same, perfectly the same, watch those light waves. You see the way the peaks and valleys overlap? They cancel and there's no light. But now if a gravitational wave is coming down on this instrument, there you can see now, hopefully. There it goes. You see the way the arms are getting shorter and longer? And that means the light waves are coming back are not aligned perfectly, and when they misalign, there's light. That's the principle of this. You use the wavelength of light, which is a millionth of a meter, to try to measure these incredibly tiny changes in the length of these arms due to the gravitational waves. So the arms are like the balloon of Einstein. And you have to do this to 1/trillionth the wavelength of light. So if these light waves don't match perfectly to 1/trillionth, you have to see this tiny amount of light.
Wow.
Yeah. So here's how not how we do it, but these are the LIGO observatories. One is in the state of Washington, one is in Louisiana. The reason we have two is if I am walking down near this observatory and I trip and fall on my face, it's going to shake the ground enough to shake those mirrors to make it look like there's a signal. So we want to have widely separated instruments to make sure nothing local causes this. And then there's there's 30 years of work to try to understand everything that could fake a signal and learn how to get rid of it. And that's a long story, which I won't tell you. So here's so we talk about a billionth the size of an atom. And what does it really mean? Here's one way of thinking about how precise this measurement is. The change in these arms of these 2.5 mile long instruments due to the passing gravitational wave is, as I said, a trillionth of the wavelength of that laser light. This is like, this accuracy is like measuring the distance from here to the nearest star, 4 light years away, to the accuracy of the width of a human hair. So imagine being able to get a ruler from here to the nearest star and be able to measure that distance to the width of a human hair. Or another way to think about it is, it's like trying to measure being able to measure the change in the height of San Francisco Bay by adding 100th of a drop of water.
Whoa.
It'll just give you a feeling of how precise this is. So, let's see what we found. Well, what did we observe on September 14th? Well, you've seen the movie, we've seen these two black holes merge together. This is the data. I just want to go over here and point at this. These data show the amplitude of the amount of light we saw, essentially, as a function of time. So first of all, I want to point out, this is about a 1/10 of a second. So this merging, when at the end of the merging process emitted strong enough gravitational waves to be seen on the Earth a billion years later, that part of the merger took about a 1/10 of a second, even though these black holes have been slowly coming together over hundreds of millions of years. The top graph is a signal from the Observatory in the state of Washington. The lower one is the one from the state, from Louisiana. This shows them overlapping, mainly to show that the signal is essentially the same in both of them. Both of them saw the same thing. This is a little bit of it, not a cheat, but these two signals have been shifted by 7/1000ths of a second, because that's the time it took this wave, which is coming in one direction, and hit Louisiana before it hit Washington. It was coming from the southeast, I believe. It fits.
Wow.
Okay, so it's incredibly violent event, and here comes the equation, the numbers. These two black holes we saw, and let me tell you when I'm done how we know these numbers. These two black holes, one was 36 times the mass of the sun, the other was 29 times the mass of the sun. And when they merged together, the resulting black hole was 62 times the mass of the sun. So the equation is 36 plus 29 is 65, which is greater than 62. So the sum of the masses of the two black holes is greater than the mass of the resulting black hole. What happened to those three solar masses, 3 times the mass of the sun? That went into the energy of these gravitational waves. This was, so you can imagine E equals mc squared, mass can turn into energy. You can imagine 3 times the mass of the sun turning into pure energy in these waves. It was a catastrophic event, even though by the time it reached us, it was these incredibly tiny little ripples. It took us decades to figure out how to measure. So, I guess I said this. But another interesting number, during this 1/10 of a second, this catastrophic event, the sort of energy emitted by these two black holes merging was about 50 times more than the energy of all the visible stars in the universe during that moment. So even though the effect here was barely measurable, this was really catastrophic. Okay, so why is it important? And I'm going to just go back over the slide I started with. It verifies the most striking prediction of Einstein's theory of gravity. Gravitational waves exists. The first direct measurement and evidence that there really are black holes, seeing a signal from the black hole itself. They come in pairs. And this is the beginning of a new kind of astronomy. And I've got 2 seconds left, so I'll finish with the fact that 3 of my colleagues were awarded the Nobel Prize in Physics this year. And we're all going to have a big celebration in Stockholm in December. So,